Okay, let's dive in. For years, really, in the world of AI, especially in natural language processing, transformers were just revolutionary.
Absolutely. Game changers.
Right. Suddenly, we weren't just, processing text. We were building these huge models, training them on, frankly, colossal data sets, and the performance just went through the roof. Levels we hadn't really imagined. They completely changed how we worked with language.
Hmm.
But here's the interesting part. While transformers were taking over NLP, computer vision was kind of marching to a different beat.
Yeah, it was still very much CNN territory, convolutional neural networks.
Exactly. Those architectures built specifically, layer by layer to scan images, find local patterns, build up complexity. So the big questions started bubbling up.
Could these incredibly powerful language models, these transformers built for sequences of words,
Right. Could they make the jump? Could they actually handle images, sequences of pixels, maybe even better than the vision specialists, the CNNs?
and that is precisely the puzzle we're tackling in this deep dive, using the paper you mentioned.
Hmm.
It's got that brilliant title, An Image is Worth 16 by 16 Words.
Love that
It
title.
really captures it, because the core idea they explore is, well, what if we don't treat an image like a grid of pixels for a CNN?
Okay.
What if we break it down into smaller, fixed-size chunks, these little squares they call patches, and then, here's the leap, treat those patches like they were words in a sentence?
Okay, so that's the mission for this deep dive then. We're going to really pull apart this paper, figure out how this vision transformer, this ViT, actually works by turning pictures into sequences.
Huh.
And then the really crucial part, find out what happened when they applied a pure transformer, almost straight from NLP, directly to image recognition, especially when they scaled it way, way up, just like the researchers did.
Let's do it.
So setting the scene a bit more. Like we said, transformers just exploded in NLP. The scale got kind of mind-boggling. Models pushing past, 100 billion parameters?
Easily, yeah.
And the standard approach became pre-training on these truly enormous text data sets, like huge chunks of the internet, and then fine-tuning those giants for specific language tasks. It worked incredibly well.
It really did. Now, contrast that with computer vision back then. Convolutional models, from the early days of Linnet right up to modern workhorses like ResNet, they were the kings. They were state of the art.
Right.
Now, there were definitely some interesting attempts, people trying to blend CNNs with attention mechanisms.
Trying to get the best of both worlds.
Sort of, yeah. Or even trying to replace convolutions entirely with attention, but often using these specialized complex attention patterns designed just for vision.
Okay.
But those often hit, like, efficiency walls, or they were hard to scale effectively on the hardware accelerators we use, like GPUs and TPUs. So even with those ideas floating around, the classic ResNet-style architectures were still dominant for the big image recognition benchmarks.
So what makes this paper stand out then?
Well, I think it's the boldness of the approach. Instead of trying to invent a super complex, vision-specific attention mechanism, they looked at the scaling success in NLP. And they basically asked, okay, what if we just take a standard transformer, the kind everyone's using for text, and just apply it directly to images? Minimal changes. Let's see if that scaling recipe works here too.
So kind of a brute force approach almost. Let the scale do the talking.
In a way, yes. Let's see if scale can overcome the lack of vision-specific design. Okay, let's really dig into how they did it, the 16 by 16 words mechanism. The core trick is getting that 2D image, this grid of pixels, into a 1D sequence that a normal transformer encoder can process.
Right, because transformers expect sequences.
Exactly. So their solution: split the image into a grid of smaller, fixed-size, non-overlapping square patches, say 16 by 16 pixels each, hence the title.
Okay.
So if your image is, 224 by 224 pixels, and your patches are 16 by 16, you do the math. You end up with a sequence of 196 patches. That number, 196, becomes your sequence length for the transformer.
Got it. So you just flatten the image into a list of little squares.
Pretty much. Then each of these patches, which is still a bunch of pixel values, gets flattened out into a long vector, and then linearly projected, just multiplied by a matrix, down into a single vector of a fixed size, let's say d dimensions.
Okay, so each patch becomes one vector.
Exactly. And this step is really just like creating word embeddings in NLP. Each word gets mapped to a vector. Here, each patch gets mapped to a vector. These are your patch embeddings.
But wait, if you just flatten them into a sequence like that, don't you lose all the spatial information? Like where the patch was in the original image, top left, bottom right?
That's the critical challenge. You absolutely do. CNN knows where things are because of its structure. Flattening loses that. So just like in NLP where word order matters.
You need position information.
Precisely. So they add position embeddings to the patch embeddings before feeding them to the transformer. And what's really interesting here is they mostly just use standard, learnable 1D position embeddings.
Just 1D, not 2D for the image grid.
Primarily 1D. And they found these work surprisingly well. The model actually learned from the data embeddings that captured spatial relationships. Patches closer together got similar position embeddings. It sort of figured out the 2D layout implicitly.
Wow. Okay, so the model learned the grid structure itself.
It seemed to, yeah. Which is why maybe fancier 2D embeddings didn't help much more. Then one more piece gets added to this sequence right at the very beginning.
Ah, the famous class token.
The very same. A special learnable class token. It's prepended to the sequence of patch embeddings plus their position info. The whole thing, class token, patch 1, patch 2, all the way to patch 196 or whatever, goes into the transformer encoder.
And the idea is after all the self-attention and processing,
the final output state of just that initial class token is treated as the representation for the entire image.
So that one token somehow summarizes everything.
That's the design, yeah. That final class token vector is then fed into a simple classification head, usually just a small MLP, a couple layers, to make the final prediction, cat, dog, whatever.
Okay. And the transformer encoder itself, you said standard.
Pretty much bog standard. It's just stacks of repeating layers. Each layer has two main parts. A multi-headed self-attention block.
Where every patch can look at every other patch.
Yep. Calculate attention scores, integrate information globally. And the second part is just a standard feed-forward MLP block. Plus, you have layer norm and residual connections throughout, which are standard tricks to help deep networks train properly.
Got it. Standard blocks just applied to these patch embeddings. Now, they also mention a hybrid architecture. What was that about?
Ah, right. That was a variation they tried. Instead of feeding raw image patches directly into the linear projection layer, you could first run the image through a few layers of a CNN, get some initial feature maps, and then chop those feature maps into patches and feed those into the transformer.
So, like, let the CNN do the low-level feature extraction, and then the transformer handles the higher-level integration.
Essentially, yeah. Combining the strengths, potentially.
Okay. And what about training and fine-tuning?
Right. So the usual approach is pre-train on a huge data set, then fine-tune on your target task data set, which is often smaller. For fine-tuning in vision, you often want to use images at a higher resolution than during pre-training.
Okay, higher res. But you keep the patch size the same, like 16 by 16.
Exactly. Keep the patch size constant. So a higher resolution image means...
More patches, a longer sequence.
You got it. Which poses a problem for those position embeddings you learned during pre-training because they were learned for a specific sequence length, a specific grid size.
Ah, right. So how do you adapt them?
They used 2D interpolation. They basically took the learned position embedding grid from pre-training and mathematically stretched or interpolated it to fit the new, larger grid size needed for the higher resolution image.
Interesting. So that's one place where some explicit 2D knowledge, the grid structure, does get injected back in.
Yes, exactly. It's one of the few points where they manually incorporate that 2D image intuition into the model. Okay, now let's talk about a really key concept here, inductive bias.
Right. The built-in assumptions a model makes.
Exactly. CNNs have strong inductive biases baked right into their architecture. Things like locality, the idea that nearby pixels are more related than distant ones, which is what convolutions naturally capture, and translation equivariance, the idea that if you shift an object in the image, the representation should shift too, but fundamentally be the same. CNNs are great at this because the same convolutional filters are applied everywhere. These biases are super helpful, especially when you don't have endless data.
They give the model a head start on understanding images.
Precisely. Now, the vision transformer, it has much less of this built-in image-specific bias by treating the image as just a sequence and using global self-attention right away.
It doesn't automatically assume locality matters more.
Not in the same way a CNN does. Any patch can attend to any other patch from layer one. This lack of strong initial bias, well, it showed up in the early results. When they trained ViT models on medium-sized datasets, like the standard ImageNet 1K.
The million image one.
Yeah. Without lots of extra regularization tricks, they found the VDTs achieved, I think the paper called them modest accuracies, they were actually lagging behind ResNets of a similar computational budget by a few percentage points.
Ooh, okay. So initially, it didn't look that promising, like the lack of bias was hurting it.
It seemed that way, yes. That was kind of the discouraging finding. at first.
There's always a but in these stories. This is where it gets really interesting, right? The big reveal.
This is the absolute core finding. Because, as the paper says, however, the picture changes if the models are trained on larger data sets, 14M 300 images.
14 million to 300 million images. Okay, that's a different leap.
Totally different. And then comes the killer line. We find that large-scale training trumps inductive bias.
Wow, okay. So just throw enough data at it, and the need for those built-in CNN assumptions fades away.
That's what the evidence strongly suggests. The experiments are compelling. You look at the graphs and tables. ViT models, especially the bigger ones, they might underperform when only pre-trained on ImageNet 1K compared to good CNNs like ViT ResNets. But pre-train those same ViTs on the larger ImageNet 21K dataset or the absolutely massive internal Google dataset JFT 300M.
300 million images.
The performance just takes off. It climbs steeply. And when you evaluate them on a whole range of standard vision benchmarks, ImageNet itself, but also others like CFAR 100 or the ViT suite, which tests how well models generalize to different tasks.
How did they stack up?
The large ViT models pre-trained on that huge JFT dataset, they either matched or actually beat the state-of-the-art CNNs of the time, like the highly optimized ViT models or Google's own noisy student.
Beat them. A standard transformer beat the best specialized vision model.
On many benchmarks, yes. And here's the other kicker.
There's more.
The efficiency. The paper showed that these top-performing ViT models often achieved this state-of-the-art performance while using substantially less pre-training compute compared to the CNNs they were outperforming.
Wait, less compute? How much less?
They estimated roughly 2 to 4 times less computational resources needed for that massive pre-training phase.
That's huge. Better results and cheaper to train. That's kind of the holy grail.
It was a really striking result.
And they dug into the scaling too, right? Like how performance changed with model size and compute.
Yeah, they did a proper scaling study. Generally, VLT models showed a better trade-off between performance and compute cost compared to ResNets across different sizes. They looked at scaling width versus depth versus patch size.
What did they find there?
Increasing the depth, adding more layers seemed to give the biggest performance boost for a given amount of compute. And interestingly, making the patches smaller, which means longer sequences for the transformer, also gave solid improvements without blowing up the parameter count too much.
Okay. And those hybrid models, the CNN transformer combos?
They showed a slight edge at the very small compute end of the scale. But as the models got bigger and had more data, that advantage vanished, and the pure ViT models caught up and often surpassed them. Scales seemed to favor the pure transformer approach.
Fascinating. Okay, so that's the amazing performance, surprising efficiency, especially at scale. But how? How is this thing designed for language actually seeing? Did they look inside the box?
They did try to analyze the internal representations, to get a feel for what it learned.
What did they see? Like those first filters that process the patches?
Right, the initial linear projection layer. They looked at the learned filters, and they found they resemble things like Gabor filters or Fourier basis functions, basically sensible building blocks for representing the basic textures and shapes within a patch. Which makes sense, right? That first step needs to encode the patch content efficiently.
Okay, that seems reasonable. What about the position embeddings? You said the 1D ones learned 2D structure.
Yeah, they visualized those learned position embeddings. And sure enough, embeddings for patches that were physically close together in the original 2D image grid ended up being more similar in the learned embedding space.
So it learned proximity.
It learned proximity. And it even seemed to capture the row column structure. You could almost see the grid layout reflected in the similarity patterns of the embeddings. This helps explain why just using simple 1D learnable embeddings works so well. The model figured out the important spatial stuff on its own from the task.
Okay, cool. And then the core of the transformer, the self-attention. How does that play out with images? They looked at how far patches were looking for information.
Exactly. They measured something called attention distance. Think of it like, for a given patch, how far away on the original image grid are the other patches that this patch is paying the most attention to? It's kind of analogous to the receptive field concept in CNNs.
Right, how much of the image a neuron sees. So what did they find about attention distance in ViT?
It was really interesting. In the lower layers of the transformer, they saw a mix. Some attention heads were already tending globally, looking across the entire image right from the start.
Wow, okay. Different from a CNN's small local fields early on.
Very different. But crucially, other heads in those same early layers were highly localized. They primarily paid attention only to nearby patches within a small window.
Ah, so maybe that's doing the job of early CNN layers, finding local features first.
That was their hypothesis, that this learned localization in some early heads might be serving a similar function. Then, as you went deeper into the network, the average attention distance increased.
So it starts looking further afield.
Exactly.
Yeah.
By the later layers, most attention heads were attending very broadly across the image, integrating information from all over to build up the final representation.
Okay, that paints a picture of how it might be processing things. Did they visualize the attention itself? Like where the model looks for classification?
Yeah, they looked at the attention maps specifically from that special class token back to the image patches. And these maps clearly showed that for a given image, the class token was focusing its attention on the semantically relevant parts of the image needed to make the correct classification.
So if it's classifying a cat, it's looking at the cat parts of the image.
Pretty much, yeah. It confirms the model is learning to ground its decision in the right image regions. And just to quickly circle back on those hybrid models.
Right, the CNN front-end ones.
Yeah, just to reiterate, they had that slight edge maybe when compute was very limited, but as you scaled up the pure ViT, that advantage really seemed to disappear or even reverse. Scale favored the pure approach.
Got it.
They also touched briefly on self-supervised pre-training, trying to train ViT without needing millions of labeled images.
Like BERT does for language, masking words.
Exactly, analogous. They tried masking out some of the image patches and training the model to predict them.
And how did that go?
Well, it showed significant promise. A ViT pre-trained this way performed much better on ImageNet than one trained just from scratch. It achieved, I think, around 80% accuracy.
Which is pretty good, but how does it compare to the supervised pre-training?
Still a noticeable gap. The same model pre-trained on the huge supervised JFT dataset got significantly higher accuracy, maybe around 84% or more, depending on the exact setup. So self-supervision worked, it helped a lot, but it wasn't yet closing the gap with massive labeled datasets. That remained an open challenge.
Okay, so looking ahead then, based on where this paper left things, what were the next big steps?
Well, the paper itself pointed out the need to adapt ViT effectively to other core computer vision tasks beyond just classification. Things like object detection, drawing boxes around objects, or segmentation, classifying every pixel.
Right, because the paper focused mainly on image recognition. Although, wasn't other work like DETR already using transformers for detection around then?
Yes, exactly. Work like DETR showed the potential was definitely there. But adapting and optimizing ViT specifically for those tasks was still a key research direction.
Makes sense.
And of course, that gap in self-supervised learning performance was a big one. There was clearly a need for more research into developing self-supervised methods tailored specifically for vision transformers to try and match that incredible performance you get from giant labeled datasets, but without needing the labels.
Yeah, because getting those massive labeled data sets is expensive and difficult.
Extremely. And finally, given how central scaling was to the whole story,
Just keep making them bigger.
pretty much. The results strongly suggested that further scaling of ViT models, more data, bigger models, was likely to lead to even better performance. So if we wrap this all up, pulling together the key takeaways from this deep dive into the source material, the most profound finding, I think, is that a standard transformer architecture, something fundamentally designed for language sequences, can be incredibly effective even state-of-the-art for image recognition. Its initial lack of those built-in CNN biases, like locality, well, turns out that can be overcome and even become an advantage if you train it on truly massive data sets. Scale really can trump inductive bias, as they said.
And with that amazing side benefit the efficiency win. Achieving that top-tier performance often required significantly less compute for pre-training compared to the best CNNs at the time. That's just remarkable.
It really shifted the landscape.
It definitely did, and it leaves you with a really powerful thought to consider, doesn't it? This paper provided such strong evidence that maybe, with enough data, the need for architectures to have those specific built-in domain assumptions like image biases for CNNs might actually decrease.
The model learns what it needs directly from the data flood.
Exactly. The patterns emerge from the data itself, and maybe at massive scale, learning directly is even better than having the bias baked in. So the thought I want to leave you, the listener, with after this deep dive is this. What could this principle, this idea that large-scale training trumps inductive bias, mean for other areas, other fields, other types of data beyond images, where we currently rely heavily on specialized architectures with built-in assumptions? Where else might scale rewrite the rules?